fast, so I'm going to start. So hello everyone, I'm Paul Evans, Leo usually on IRC, P. Evans on CPAN, etc. This is actually a talk that I've done once already, but I did this at YapCEU in Granada this year, and the projector decided not to like my laptop, so we spent the first 20 minutes looking at this screen, and then the remaining time was all screwed up because I was in an annoying mood because of the projector and so on. So I didn't really do it properly. Also, it wasn't video. Well, I don't know, is it going to be video this year? It might be.
It is supposed to.
There's a camera. I don't know. Maybe it's recording. Who knows? But anyway, hopefully this one will at least be better. The only slight difference is Larry didn't actually come to this one last year at EU, but he seems to have been wheeled out now. So never mind. Oh, I'm sorry. Okay, so this is basically me talking about why Perl 5 kind of is and isn't a scheme. And to do this talk, I'm going to make it slightly easier in my head to conceptually divide the audience in half. So to you people over here, I'm going to presume that you're Perl programmers, and I'm going to talk to you lot when I'm talking about scheme, to tell you what scheme is like. And you half on this side, I'm going to presume you're the scheme programmers, and I'm going to talk to you lot when I'm talking about Perl. So I'm going to start with this side. Sorry, it's been a while since I've done this, so I might have to occasionally remind myself what I'm actually talking about. So, scheme. Well, what is scheme? You need a specification designed language. Unlike Perl 5, there's a spec, there's a written spec. The first specification was the report on the algorithmic language of scheme, and then it was the revised report on the algorithmic language of scheme. And then they came up with this exciting idea of putting a little superscript n in the number, because that makes everyone happy when they want to type the name of it. So currently we're at number 5. Well, actually I'm not sure this is true anymore. 5 sat around for a very long time. A whole lot of people went off and designed a 6. It kind of went sprawling a bit out of control. And then some people said, let's ignore 6 and skip straight to 7. Which is a strategy to solve that problem. I think it's the only one. 7, they've split up into 2 halves, and there's a small one and a large one, and it's a thing I wish somebody would do with C one day. But never happened, because C is just getting huge and needs to be split into the sort of the small bit and the library on top. Anyway. So, some simple scheme for you people. So, this is a little example of a nice little REPL. So we can type in a command here, like 1, 2, 3, and out pops the result. It probably won't surprise anyone to realise that if you turn 1, 2, 3, it prints the result 1, 2, 3. It probably won't surprise anyone to know if you type a string, it prints you a string. You know, so these are just values and they get printed. Now, this is a function call, it's key. I'll come back to this later, but basically it's important to pronounce these right. I pronounce this as the sum of 10 and 20. This is, that's the name of the function, there are the arguments, we call it, we get a result. No great surprises. Again, no great surprises, we can test these, look. So we can have the sum of 10 and the product of 4 and 5, which is also 30. That clicking noise is getting really annoying, but I don't think there's anything we can do about that. So I'll just have to be more exciting and interesting than the clicking noise. So, what else can we do? We can define named things. So we can define our new name of 1 has the value of 1, and then we can use it as if it was the value 1. And so this will not surprise people. That means 1. It will not surprise anyone to note that I can add it to 2 and still get 3. And then this other form, next. Quite exciting. Now next says, here's a little body, we're going to define some names, give them some values, and then we're going to run this chunk of code. And that's a local name inside solid. So inside that body, TWO has the value of 2, and if we had another statement cat here, we would no longer know what 2 is. It's a, let's please go. We can define functions. This is very exciting. Look. So we've got this function here called add 1 to x, and there's this definition body. And it will probably not surprise anyone to know that we can call it like a function. Remember, as before we had this plus here, that's the name of this function. We're calling. Here we can just call the function, we can pass 2 in, and out pops 3. So, great surprises. can call map on, we can pass in the function as a name, and it just comes in as the identity of its function itself. We're not calling it, we're just passing it in on this list of 1, 2, 3, and outbox, 1, 2, 4, outbox, 2, 3, 4, 5. Then go to prices. So then puts u-lot. In contrast, Perl is an implementation-defined language. There's not really a written spec, it does what it does. That's defined as what it does. The canonical, the only implementation shipped by group of people hooked up by quarters, UOP. This slide might be out of date. Someone can probably shout if it's wrong, because I think that too is probably bigger than 5. It's 5 now, is it? Wow, 5, 303. Okay, so that's 523.5 now. And possibly there's a 522.1, I can't remember. Not yet. Oh, I like the word yet. But anyway, so that's where we are, version-wise. And just as a little contrast, to show you no trickery, look, we can do the same examples as before. We can have 1 to 3, we can have hello world, we can have 10 added to 20, we can have 10 added to 4 multiplied by 5, we can give names to things. These are all exactly the same examples as before, but in a different language. And there we go. This screen. And we can define these named functions. Again, I'm sort of cheating. Imagine there's a use 5.20 up there with a signature-y thing, because that just makes the examples actually fit on one line of the screen. We can define these named functions, we can call them, we can call map on them. It's a bit trickier syntax, because naming, simply putting the name of a function in Perl calls the function with no arguments, which is sometimes useful, but once you start doing lots and lots of functional programming, quite often in functional programming, you want to refer to a function rather than call it with no arguments. So it's a little bit more awkward in Perl to just talk about a function without actually invoking it. It's like talking about someone in the room. They sort of look up and go, what does that mean? So you kind of have to do some hushed tones. So what do these have in common? Well, they're both dynamically typed. So is the same, as close to the same example in both languages. What we mean by dynamically typed. This is one of these phrases that people often throw around, and sometimes people don't quite understand what they're thinking about. If we just look at the function itself here, we're defining a function. The function is called ID. Here we're also doing the exact same thing. We're defining a function called ID. It takes an argument called x, and in its body we're simply returning the value x. Now, at no point in the definition of this function have we said what kind of thing x actually is, what its type is. It doesn't care. The language doesn't care what type it is. It will do whatever is necessary to return that value, and it will do that at runtime by looking at the type of the thing. That's what dynamic means. It means things you only know by running the program. You cannot look at the source code and see what type it is. That's what dynamic type means. So both languages are dynamically typed. And we can see we have a little example here where we're constructing a list by putting a list function. And we're just having a few little examples. Here we put the identity function on 10, and on a string, and on a sublist. And in each case, it just copes by returning the same things. And the Perl example does exactly the same thing. So the function really doesn't care what actually passes through. To the basic fact. They both have lexically scoped variables. So as I said, this thing called let creates a variable. Actually, it occurred to me the other day, this is not the best example, because it also shows dynamic scoping, but never mind. We define a variable called s and we put in value. And then inside this second block here, we've defined the same value, the same name of s, and given it a different value, and then we've asked to print it. There's a function called display that just prints stuff. And we display the name, the value of this variable, and then we display it outside of the block, and it has different values in each value. It should, and somebody pointed that out in Granada, and I forgot to update the slide. Thank you. Someone is awake. This is excellent. At least one person is awake, other than me. I presume I'm awake. Yes, it should indeed be Bafu, as should that one, yes. I probably had something else in mind when I was writing this, I don't remember. So again here, I've tried to do, Perl doesn't really have this let thing, but you can sort of treat it as a little block where you define some variables, blah, 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 and then when you fall out of the block, this variable disappears. And so anyone else sees the one that was there before it. And that's what this depth thinking does. And I'm going to keep talking about depth. It's an example of something very powerful, which I can get to in a bit. Now again, they both have what are called first-class functions. First class means it behaves like a value. So in pretty much every language I can think of, numbers are first class. You can just treat them as a single atomic value and you can pass them around. In most languages you can't see, strings are first class. You can just pass them around as if they were a thing. You can make new ones and return them and do anything strings can do. Languages like Perl and Scheme, functions are first class. So we can actually just create this idea of a function with this keyword random. And what this is saying is, create me the idea of a function, and this function should take one argument called x and return this thing as the body. And we're just going to treat the value directly. We're not going to bother giving it a name, throwing it on the symbol table or whatever, because we're only passing it in filter, right? So it doesn't need a name. Now what this particular filter function does is tests if x is greater than 0. Again, this is one of those things that Scheme has where you look at it and initially you think, the things are all in the wrong order because I wanted to see the greater than sign in there. But this again is like the add function, for example. Add, you can pass in as many numbers as you like, and just sum some more, so you're not restricted to 2. This is a wonderful function. What this function actually tests is, have I given it a list of numbers that are decreasing in sequence? So normally you can call it 2, you can call it with 3 or 4 or 20, whatever. So anyway, what we're doing here is we're filtering for all the numbers that are greater than 0. And again, here's a similar example in Perl. Technically, if you stare at the image long enough, you realise that this thing here isn't really a function, it's this kind of deferred expression block thing. But pretend we made a different thing called filter and gave it a prototype or something. Because grep map is strange and weird, but most things you can pass real functions like that. Now they have some very similar features. Now I got to about this point in the talk in Granada when Larry was around, and I said, so there's a bizarre thing in Perl that's very similar to Scheme. Is that some grandmaster designer or pure coincidence? And he gave a very boring answer. He said, oh, he didn't know about Scheme at the time, so it's a pure coincidence. Which I thought was very unsatisfying, because I wanted this to be a very subtle and grand plan. So, in Scheme, if you put a name at the beginning of a list like this, that's how you call a function. What this little parenthesis syntax means is, I'm going to put a function. Here is the name of it. But here, this would try to call a function called hello and pass it the value of name as an argument. Well, we don't really want to do that here, perhaps. Because maybe we wanted to talk about a list that had 2 things in it. Because it turns out that you want to do that quite a lot. So rather than having some exceptionally awkward syntax, we have this little quote mark that says, whatever's inside these parentheses, and it could be a huge great tree of stuff, just treat it as a value. Don't try to evaluate it. It's called a quote. Because it's a quote mark sign. And so what this does is literally gives us the thing back. And it's equivalent to, you can call it as a function called quote, but you really must be called that. And it's exactly the same in Perl, sort of, in that we have the single tick quote mark to say, look, here's a bunch of characters. I don't want you to treat them as program code. I just want you to treat them as a string. And funnily enough, it comes back exactly as a string. In Perl, you can only do it with a bunch of characters and you get back a single string. Whereas in Scheme, you get a whole deep tree because you properly understand the tree shape structure of your program. It's not quite the same. It's very, very similar. And again, we have this thing called Q for doing that. And then there's something called quasi-quoting, which uses other fancier symbols. So we have the backtick and the comma, and it kind of looks a bit weird. And you sort of look at that and you kind of wonder, what on earth is this? This is absolutely bizarre. Except you realise we have the same thing in Perl. Because if you use double quotes, then anything that starts with a dollar sign, we say, we're actually going to evaluate that. So we're going to pretend that we hadn't quoted this little inner part of the thing. And its proper name in Scheme is quasi-quote. And its short name in Perl is QQ. And it was at this point that I said to Larry, look at that, the quasi-quote has QQ in it, and in Perl it's got QQ. Is that some grandmaster plan? And he said, oh no, I didn't realise that. That was just a coincidence. So I was very upset. So I'm almost wishing I hadn't asked him that, so that I could go on believing that was brand design.
I have a question.
Hmm?
In the previous slide, you had a space before the comma. Is that necessary syntax?
Yes. So Scheme, the Scheme. I didn't really mention this earlier. Scheme cares about spaces between things, definitely. White space. It doesn't matter what white space. Doesn't matter what white space, but you need some white space between things so that Scheme realizes they are separate things. And parentheses are important, and these symbols are important. That's about it. In fact, I'm going to get onto that in a brief moment. So yeah, I'll come back to that.
So, if you go back one slide, again. So basically the backtick is like a TW in Perl, and the comma is like if you could put a dollar in there.
It's not so much QW. It's literally like double quote.
Yeah.
In that inside here, mostly we're literal, but we have this effectively this dollar sign where we can say, here's a thing that I don't want you to treat literally. I want you to do something special with it. And you can also use an @ sign, and there's other weird things that we have later in strings. But by and large, yeah. So it's like that. So things that are different. In Scheme, there are a bunch of types, things that the language understands, which are kind of similar-ish to things we recognise in Perl. So we have strings. Recognize those. We have these things, he calls them procedures, but functions, whatever. The concept of a Boolean is an actual thing in the language. And Scheme has this slightly odd property that, like Perl and C and a lot of other languages, you can test the truth of anything. So you can always ask something, is this true? And in Scheme there is exactly one value that is false. And that has the name false, hash F, like that. So hash T is true. They're literally a Boolean variable. Boolean value, whose name is true, and it is true. False is the only thing that is false. Everything else in Scheme is true. Even an empty list, even the number 0, even an empty string, they're all true. Which has some useful properties sometimes if you're kind of filtering and you want to find something and then return the thing you've returned, otherwise return false. It means that if you happened to find a 0 or an empty list or whatever, and that was the result you wanted, it's still true. And the only thing that is false, but you have to hope that you weren't accidentally looking for a false or something. So, but it can be. Scheme also has these things called symbols. So, just a bunch of characters like that on its own. As far as the syntax of the language is concerned, that's just a symbol. It doesn't really know much else about it. Perhaps later when it runs the program, it might use that symbol as the name of a variable or a function or something. But the language is very clearly defined that there's just a symbol and it's just a bunch of characters. And those are very useful. As compared to Perl, we have undefined things, we have defined things, and they're sort of sloppy, so match things or numbers, sort of the same thing. And then we have all these class references. I put dot on top because there's a whole bunch of other basic weird things. But that looks quite interesting. Okay, so in Scheme, these symbols stand for a thing, and the thing that they stand for is always part of the same, what's called a namespace. So at this point, you see an X, you always know there's only one kind of X at this point that we could have. So earlier on we had X as a number, and then later on we've decided that X is actually this function. But they're still kind of referring to the same X, because we've kind of overridden that. As compared to in Perl, where we can have a scalar variable of an X and an array of an X, and a hash of an X, and a function of an X, and a go-to label of an X, and a file handle of X, and there's a couple of other slightly odd ones, I think, but then it starts to get a bit ambiguous as to exactly which ones are what. But the name X could mean about 7 or 8 different things at the same time. And these are called namespaces. So this is a very different thing to Scheme. And incidentally, this thing is one of the things that makes Scheme different from a lot of other list-shaped languages, in that Common Lisp, which is the other kind of big family of Lisps, decided that they would have 2 namespaces. So, like in Perl, where we have a namespace for functions and a namespace for variables, they have the same thing in Common Lisp. Which is sometimes useful in that if you want to operate on a list, you could store the list in a variable called list, and that wouldn't necessarily conflict with a function that is called list that returns you a list. But I think it makes the language a little bit messy, because it's kind of nice that if you see the name of the thing, it refers to the same thing. So, just as a brief summary of what we've seen, parentheses always invoke a function, so you put the name here at the beginning, and I'm going to go there. There aren't really any infix operators, everything is just a named function, so we can add things, we can add lots of things, we can test if a numbers form a non-decreasing sequence. As I said earlier, the comma is a bit of a strange thing, the comma and the backtick and so on. But otherwise, almost every other character is valid in a symbol. So there are a lot of naming conventions in Scheme. So for example, any function whose name has a question mark at the end of its name, that's what's called a predicate function, it tests whether some condition is true and returns either true or false. You have a lot of functions that convert from one type to another, so tend to name them with this with an arrow. To say, yep, I take a number, I return a string. And you also have a lot of functions that have an exclamation mark in them. And I like, the exclamation mark is one of my favourite ones. Almost all of the core language functions don't mutate anything. They just take values and return you a result. So they're kind of pure functional ones. And so Scheme is mostly this kind of pure functional language where we say, look, mutation is kind of bad, try not to do it. But the language gives us a few ways out of that, because sometimes if you have a big data structure and you know kind of you're the only one who's got it, or you want to do something weird and special, you kind of think, it would be nice if I could just mutate that. So there are a few little mutation functions around, but they all have the exclamation mark on their name, kind of warn you, look, I'm going to modify something. I'm not just going to return a new thing. I'm actually going to do some changes. So kind of be careful. So that's what exclamation mark is. And this is one naming convention that everyone uses. I don't know what it started with, but quite a few of the core parts of the language have this star in their name, which is a sort of a variation on a theme. So the plain let is a bunch of names and a bunch of values. And it creates a bunch of new variables with all those values. And then runs a function. But sometimes you kind of want to do it slightly differently to that. So there's a very slight variation on a theme with let star, which says, we're going to give this list of variables, but we're going to definitely do the first one first. And then having done the first one, we're going to do the second one. And then having done the second one, we're going to do the third one as well. So we definitely can do them in order. But if the order didn't matter, then you could use the not star version. And in the language, there's quite a few pairs of functions that there's just a slight variation with a star on.
But this is like purely convention. The actual
Yes.
interpreter does not look at
Oh,
it.
absolutely, yeah. The same as on this slide. This is just pure convention. But it's a very deep nested convention that library authors and so on will basically tend to follow.
Right.
So that you can just look at the function with name ends in a question mark, and you know that I'm just going to pass it one thing and it's going to tell me some truth about that thing, and it's not going to modify it and so on. And it's a very useful naming convention to have, because it means you can just look at the list of functions and already know exactly how they're going to work. That one's not terribly exciting. But one of the ideas in Scheme is that functions tend to have the same shape, code tends to have the same shape as values. Where am I and this one. So there are a few things in Scheme that do something, like set and set apart and display, which kind of ought to have an exclamation mark maybe on its name, but it doesn't. These do a thing and don't return any particularly useful value. So like setting the value of a variable, I mean, there's no, Perl returns the variable, but mostly, this operation conceptually doesn't have a result, right? It's just done a thing and then it's done. Whereas most functions have a result, that you can sum these by values and you get value for the things like if are exciting. In Perl we have if as a control flow keyword, and we also have the ternary question mark operator. Question mark operator tests whether the first thing is true or false, and then executes one or other of the things and returns its value, which syntactically looks totally different from the if keyword, which tests the value of the first thing, and then, depending on whether it's true or false, executes one of the second other two things, but just doesn't bother returning value. And so, languages in Scheme say, well, there's no point doing that, right? Why don't we just have the if, and execute the things, and then have the if return a value? So in Scheme, pretty much everything has a return value that's actually meaningful. And there's no sort of dual case, here's some control flow things, and then here's some functional things that return values in a separate way. They're all combined together. So it makes for a very small, neat cut down language. As compared to Perl, I'll just go through these quickly because these are all fairly obvious. You have expressions, you have statements. You can tell a statement with a semicolon at the end of its name, apart from sometimes when statements don't have semicolons on. And most things return values, apart from the ones that don't, except if you put them in a do block and then they do return a value maybe sometimes. It's a big deal. So Perl's a bit messy. Here we have this do thing. Do is a wonderful thing that any language that has an idea of statements and expressions separately really ought to have a thing called do. Because there are so many times I've been writing Python code and I thought, I really want this do block. I want to have a bunch of statements here, but then use the combined result of them as an expression to do something else with. And that's what do does. And it's really, really useful. It's a thing you don't need to do in Scheme because Scheme just works like that. And that was really annoying. Because it means you can do things like this. You can just say, well, look, notionally I wanted a value here, but for annoying reasons like the author of this code happened to forget that setup probably ought to return the value itself so that I can use it as a changing mutator, blah, 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 blah. I have to do this thing. And things like this little 3-line block turn up quite a lot. And they're really easy to put inside do blocks. And in Scheme you don't need to because they're just there. So, in summary, that's Scheme, right? People who go on about Scheme go on and on and on about the fact that that's all that there is to Scheme. Because all you need is these kind of 6 little things, and you can just combine everything else up, and you can make anything. Provided you have macros, because this is the core thing that makes Scheme a Scheme. Functions take a value and return a result, and the value that they take is data. The result that they return is data. But in Scheme, programs kind of look a lot like data, right? So if you had a function that could take some code that happened to look like data, operate on it at compile time within the compiler, and return a result that looked like data that was actually code, then you've got a way to write a program that can change itself into a different shape. Which means we can extend the language. Because if this was all our language was, that would be really, really awkward and painful to write. It would take ages to do anything useful. But if you want to implement a language, you can write that in like an hour, right? I mean, you can just implement these things and then have it. But nobody could use that scheme because it would be horrible to write code in. So you have these things called macros. And there's a whole syntax for these things. This is a huge long one, so I'm not going to go into great detail about it, but I'm just going to say this is a thing that you can do. So there's a thing called define syntax, which says, I'm going to define a name of a thing and here's its value. But I want to do that sufficiently early that the compiler can see it and use it, because I'm defining some new syntax. And so this syntax says let. So we're actually defining what let actually does. And here's its value. And its value is this big, long, pattern-y thing. And that looks kind of big and scary, because, hey, there's like 4 close parens here. I think that's crazy. So I'm going to make that a little bigger for you, so it's a rat. And I'm going to kill that bit, because that's not the value, right? That's just saying we're defining it. So what it really is a pair of a pattern and a template expansion. And what this macro does is says, look, if ever you find a pattern that looks roughly like this shape in your program, rewrite it so that it was this shape instead. Which is kind of like a substitution. So with a slight bit of abuse of Perl notation, I'm going to say, well, look, this macro kind of behaves like this. So what we're saying is, look, if we find a structure that looks like let, and this sequence of one or more names and values, and then this body at the end, then replace that with somebody defining a function that takes all these names as arguments and executes the body, and then apply that function to the values. So what we've got now is a nice, short, neat little rule that says, allow me to define this new syntax that wasn't part of the core language, but is really useful, and rewrite it in a simpler form that the core interpreter knows how to execute. So, for example, if we want to do one of the examples I showed earlier, where we say let 1 have the value 1, and then display sum of 1, 1. Language doesn't know how to do that, but it has a macro. So it goes, okay, I'll rewrite that into something I know. So I'm going to define a function that takes a parameter, and I'm going to store it in 1, and then display blah, blah, blah. And then I'm immediately execute it with the value 1, which would be very similar to doing this in Perl. So it's sort of like, the core language doesn't really have variables, and doesn't really have nested scopes and variables. All it really has is functions. And kind of almost everything in the language is just applying functions to functions and more functions and more functions. Everything is a function. And if all your things are functions, you get very good at being able to implement these things really efficiently. Because, for example, nobody would do this in Perl, because that's crazy. Executing a function takes like hours. So you would never really do that in Perl because it's very slow. Because nobody does it very often. But if that's literally the only thing your language does, then you can make it very small, very efficient, very, very, very fast. And turning programming into lots of very big structure that looks like this, the thing runs very efficiently. It's still really powerful. Because in that set of things here, you might notice that nowhere did I put a while loop, a for each loop, a map, any of these kind of iteration things. Because it turns out you can do all of those. So iteration is basically doing the same thing multiple times on different data, which is kind of the same as recursion, right? I mean, we're doing the same thing lots of times on different bits of data. And so what Scheme decided to do was say that there's no point writing a while loop when you could do the thing as a named function, and then if you want to do it again, call it back on itself. Because we already know how to call functions, that's really efficient, right? So let's just do this, because it turns out that's good enough. And so it looks like this in Scheme, where we say, find function, give it a name. I decided to put same there because it makes it look like a Perl code. And then if the loop condition holds, we'll do it again, and then call it. But actually, that's a bit messy. We can write it even better. So the actual form in the language of let is not the simple one I showed earlier. It's huge and complex, and I'm not going to go into it because it's out. But it also lets you name the body, and it's visible within itself. So you can do this kind of self-recursion thing, which is quite huge. And so, again, with a macro, you suddenly have recursion made up out of a macro, because, hey, so there's a bunch of other things that you can do. You can also, I've never really seen why, but there's a thing called let syntax, which is like let, but it's syntax style. And there's lots of other things that are called dash syntax, which is very similar to begin. Because in Perl you have these begin blocks that say, here's a bunch of code, do it in the compiler. And I couldn't think of any particularly short, simple examples, so here's a kind of very long one. But that's kind of how begin works. How long have I got? I think I've got about 15 minutes. So Scheme has this very clear distinction between compile time and execution time. In a scheme program, you have a compiler which takes the source code that you've written and turns it into a kind of simpler form by expanding on the macros. Because all of these crazy macros are very crazy and weird, and maybe half of the program is written on macros that your programmer wrote last week while he was more and drunk. The language isn't going to understand, though. It doesn't matter. Throw in the compiler. That turns it into a much simpler collection of basically those fundamental forms. And that's all you need to execute the program. The interpreter then implements it. Because it's very small and very simple. There's not much to do. Because it's only those fundamental forms you can do variation. Perl kind of has the same thing, where we take the source code, we compile it into a thing called an octree, which kind of represents the source syntax, but kind of doesn't, and doesn't really have a way to represent the syntax separate from the semantics implied by the syntax. It's a bit of a shame. But it's very similar. And we have these begin blocks, where we can put some code to actually run. Because in Scheme, you have a compiler, which is a program, and then probably separately, you have the runtime. Sometimes people put them together. But the core definition of the Scheme language allows for them to be separate programs. Whereas in Perl, we know that the compiler and the runtime are part of the same thing, and so they can interrupt each other. And so sometimes your begin blocks can actually do things. Like you could have a begin block that started up an HTTP client and then grabbed some file off the internet and looked in the file, and depending on whether the file had a 1 or a 0 at the end of it, it might compile a function one way or another, right? So you can extend the language in fantastically bizarre and flexible ways, but it means you have to have a runtime in the compiler and vice versa. Whereas Scheme, slightly more simple, very much restricted to basically pattern matching and template expansion, but it allows you to split them up. Because the core rationale for Scheme, and I'm just going to quote directly the first paragraph from the Scheme spec, it says that programming languages should be designed not by piling feature on top of feature, but by removing the weaknesses and restrictions that make additional features appear necessary. Because what they started doing for Scheme is that they started writing up a whole load of things that they thought the language should have, like a map and while loops and named functions and all this kind of stuff. And then, as they started implementing it, and they got as far as started to implement macros, they suddenly realized, actually, there's no need for the core language to define, for example, a while loop. Because you can just build that out of a macro. So take that core language. And the more they did that, the more they got good at actually noticing, we don't need to define any of these things. Because if you just take these little tiny pieces and stick them together in the right way, you can make a language. And it's a very powerful concept. Like, Unix is built like that. A lot of other things are built like that. This thing, for example, everyone knows what this is?
Yeah, don't step on it.
Of course you do. 3001 in red. This is Lego. I mean, everybody knows Lego, right? Lego is this wonderful metaphor. It's far better than a plastic children's toy. If you want your children to grow up as engineers, buy them Lego. Seriously, it's wonderful. Do not buy them this Lego. This is bad Lego. This is what I call bad Lego. This is not Lego, right? This is a plastic toy that happens to fit the 8mm stud pattern. This is a very special purpose thing. This is like some fancy, weird program that you buy for several $1,000s and can only do one exact thing. If you want it to do something slightly different, you have to fill in some paperwork and send it to California, right? This is good Lego. Look at that. This is lots of little tiny things that you can stick together any way you like. It's kind of like so speaking of CPAN, Scheme has this thing called SRCS. So CPAN is the comprehensive Perl archive network. Lots and lots of Perl code. It's very comprehensive. It's got over 32,000 modules. That number's probably out of date already, but it's probably at 33 by now. It's got a bug tracker and content repo, and wiki annotation, smoke testing, and code coverage tool, which has been added since I drew this slide, and basically tons of stuff. It's really cool. The SRCF, the Scheme requests for implementation, it's pretty capital F. Whoops, never mind. Second, the SRCF has about 120 suggestions that people who implement Scheme might want to consider putting into their Scheme interpreters. Because don't forget that the Scheme is a standard. It says, here is how you should write your thing. Scheme is a piece of paper. It's not a program. People go off and implement Scheme interpreters. And then people went off and implemented lots of little ones. And put more and more features in, and then started putting in different features. And then it became very tricky to write an actual Scheme program because you would target it for your interpreter, but then it would be different from everybody else's interpreter, so you have to use the right interpreter. So in effect, people don't really write Scheme programs. They write programs for Chicken Scheme or NZ Scheme or Rapid or whatever, and then maybe one day think about porting it, but in practice we don't. And that's one of the things that Scheme R7 is trying to fix, actually, is saying, yeah, we kind of screwed up. We should have given you more ideas for lots of rich features to put in, but we didn't want the implementers to implement that. So that's why they came up with the split between R7 small and R7 large, which is basically saying, if you want to implement Scheme, actually build an interpreter, implement the small one. If you want to write a Scheme program, write it to the large version, because the large version can be implemented as a standard library on top of the small one. So that's their plan, and that's what I think C should do as well. So anyway, in summary, so I presented lots of things that are in Perl, I presented lots of things that are in Scheme, some differences. So things that I think Scheme ought to learn from Perl. First of all, CPAN. First of all, frankly, this could be this word doesn't have to be Scheme. This could be any other language ought to learn from CPAN, right? CPAN is just so much better than anything in any other language because it combines so much tooling. There's so much stuff there. Oh yeah, there's a bunch of code that people have written. You know, there are more Ruby gems, there are more Node.js thingies, whatever those are called. I can't remember offhand. But they don't have the huge cross-coverage features that we have on CPAN. Scheme kind of forgot to define associative data structures of any kind. The spec kind of points out that your library might want to provide you a function so that you can have a list of pairs, and in each pair you sort of have a key and a value, and so you've got these sort of standard functions to say, find me the value associated with a key that looks like this. But that's a linear search, it's a bit slow. There's an SRCF about doing associative data structures and hashes, but it's not really part of the core language, and it gets a bit lacking sometimes. So it'd be nice if we had those. It would be nice if some scheme defined maybe an optional way to put real code into your compiler, because there are so many times that just doing pattern matching or expansion is not enough. You need something fancier. And almost any actual scheme implementation kind of defines its own fancier ways to do macros, and they're all different. And meh. It'd be nice if there was a standard. The things I think Scheme could learn from Perl could learn from Scheme is the flexibility of having lots of little parts and gluing them together. We're starting to get that way with CPAN. Things like PSGI is a great example here, where before PSGI came along, people wrote web apps that ran on a web server, and then maybe some of the fancier ones you could run on two different kinds of web servers or something. And what PSGI showed you was that, no, these are different things. There's web servers, there are web apps. These are two separate worlds. Why don't we define a standard way that we can talk between one and the other, and then you can use any kind of web server with any kind of web app. And there needs to be a lot more of this in Perl.
Something like roles would probably apply to this.
Pardon?
Something like roles.
Roles. Oh, roles. Possibly. I mean, so roles are kind of think at the small scale. In terms of, I want a class that does A and B, so I'll kind of add A and B as a role. I'm thinking almost at the application sides of things. More things like DBI, like PSGI, like that kind of thing. It would be really nice if people stopped gluing too many features together in one module and start splitting them apart. Because the smaller pieces you have, the easier they are to implement. And if you define the border between the things, it gets much easier to see what is this thing that I'm making. And also something that I think Perl needs at some point relatively soon, and I keep threatening to do it by Easter, you know, it's a bit like Perl 6 and Christmas, you know, maybe 1 year. I keep threatening to have some kind of macro-y thing, some kind of way that you can tell the compiler, you can write a piece of Perl code and tell the compiler, when you see some other code that seems to match this pattern, call me and I'll turn it into something you can understand. That's something I think we need because people keep trying to extend the language, and it'd be nice if you could extend the language from Perl. And that's kind of it. So we have like 5 minutes. So maybe any questions? Oh, so hello.
Hi. Do you have any recommendations on which scheme would be a good one to play around
Oh
with?
God. Which scheme is a good one?
Sorry, this.
So people seem to like Racket. Racket is one of these things where if you know Scheme and you want to write a really big, powerful Scheme program, you can probably find all the features you want in Scheme in Racket, because Racket is huge and awesome and has everything. But if you want to learn Scheme, Racket is huge and awesome and has everything and will scare you, because you have to know what a prompt is, and maybe one day I think it's a Scheme equivalent of a monad, I don't know. It's this sort of scary word that you have 17 tutorials and then one day you understand what it is and you write the 18th one. I don't know, honestly, if you want to play around with Scheme, write a Scheme interpreter, because you have to define those 6 things. I wrote one in Berlin now. But yeah, Racket probably is the standard one.
I've already talked a lot.
Oh, I see. Hello.
Which of the 2 languages is better?
Oh!
Both 6.
So I'm going to defer to Random Monroe here with the SKCD comic where the guy kind of goes off onto this crazy dream and realizes how neat and wonderful and pure and abstract and awesome Scheme is, and how everything can be fitted in this neat structure. And he realizes that the universe was built by God in Scheme, and then he goes to meet God, and God says, "Oh no, we designed it in Scheme, but we wrote it in Perl." Because if you just want to get stuff done, right? You can just find something on CPAN, link to something else on CPAN and call it done, right? When I did this talk in Granada, the first question that anybody asked was, do you have any sort of examples of big successful systems written in Scheme? And my answer was no. Nobody writes anything big and fancy and real world in Scheme because
Lily Pond.
Closure is being applied.
so there's
pretty well.
Lily Pond, there's people write GIMP plugins in Scheme, right? That's the thing. People write window manager in Scheme. So the window, oh, you can't see it on here, but my window manager is written in Scheme. Well, it's not written in Scheme, it's written in a dialect of Scheme called Rep, except it's not really a dialect of Scheme, it's there. Anyway, yeah, people use it occasionally, but it's a nice one to steal ideas from, but I wouldn't use it for anything. 5 minutes.
Oh, no, I'm asking a question.
Well, ask it.
Okay, so the things you think Perl needs to learn from Scheme, do you think any of those have been taken on by Perl 6?
Maybe. So Perl 6 definitely has a keyword that's called macro. I don't know what macro does. Not enough. Well, then I think Scheme macros have.
They're still hashing that one out.
Okay. Well, okay. So having macros would be very nice because you always. So also, I quite often end up wanting to do my toon equals expression return toon if expression return toon if toon, right? So I would love to have a keyword return if. Okay. But sort of, you always come up with lots of different things like that where you just think, it'd be nice if I had a keyword to do this, just to because like this is what people write named functions for, right? They realise here's a sequence of operations I want to do lots of times. I want to give it a nice cute name so I don't have to remember the whole thing, just pass it when it needs to. But named functions aren't always powerful enough. And so sometimes it'd be nice if there was a more powerful abstraction of I want to do these things in sequence all the time. And sometimes macros have to be very complex. Otherwise, what else did I say? Composable parts and easy. Well, okay, so being able to compose lots of parts together, Pulses has. Given how long it's taken me to implement them, I don't know whether this part is true. That really what you should be able to do is try to decompose it into small, self-contained pieces with well-defined edges, like Lego bricks. Like, what are the
Which we've
defined
already
edges of
decided
Lego
are a good thing.
Isn't that what rolls are?
Rolls are Lego bricks about this size, right? But composability happens at this size and this size and the size of the entire building. They're a kind of composability, but composability of individual expressions within a statement, composability of statements within a function, composability of functions within a class, composability of entire package frameworks in a program. And I'm talking out of time. So thank you. Oh.